Next is combination circuit or combinatorial circuit. So in combination circuit, it's also called as combination circuit. You have actually two types of circuit. One is combination circuit and other is sequential circuit. So in combination circuit, which we will be dealing with now, the output depends on only on the present input. Then it's called as combination circuit or combinatorial circuit. Output depends only on the present input. You give a input, a set of inputs, the output or the outputs depends only on the present inputs. That is combination or combinatorial circuits. In the case of sequential circuit, the output depends on present input and past outputs. Present input and past outputs. That is a sequential circuit. So that is the main difference between a combination circuit and a sequential circuit. We will deal with it in detail in the coming modules. So as I mentioned, in a combinatorial circuit, the output depends only on the present input. So any circuit where we give some inputs and depending on the input you get an output, that's called a combination circuit. So there are many circuits. You can design any circuit depending on your requirement. Some standard circuits we will be dealing with. The first one being a half adder. So if we know how to design such standard circuits, we will be able to design any such combination circuits depending on the requirement. So half adder. Now what is a half adder? Half adder is a adder circuit wherein you have two inputs. Two inputs means two 1-bit inputs. This is an input, this is another input. Both are 1 bits. Then you have outputs. Again, two outputs. One is sum and the other is carry. Okay. So this is a half adder. Now, since you have two inputs, see, any such combination circuit, you will know the nature of behavior of that particular circuit. So from that you can write the truth table. This is the truth table. So first of all we'll write the truth table. And how do you write the truth table? From the nature of the circuit we know how many inputs are there. So in this particular case you have two inputs. So two inputs means 2 raised to 2, that is 4 input combinations will be there. Yes, so if you have n inputs, you have 2 raised to n input combinations. So 2 inputs, the input combinations are 0 0, 0 1, 1 0 and 1 1. These are the input, all the possible input combinations. Yes, so next we'll write the sum and the carry. So what is sum? Just add the two inputs, you'll get the sum, and if there is a carry over, then that is the carry. So 0 plus 0 is 0, carry is 0. 0 plus 1 is 1, there is no carry. 1 plus 0 is again 1, no carry. 1 plus 1 is 0, carry 1. So 1 plus 1 is actually 1 0, and since this is 1 bit addition, that extra bit is taken as a carry. So that is this. Now first of all, we know how many inputs are there, how many outputs are there. So based on the number of inputs, if you have n inputs, you'll write the 2 raised to n input combinations, and after that, for each set of inputs, you'll write the outputs based on the nature of the circuit, whatever application you need. So after writing the output, that is after completing the truth table, that is first is you will write the truth table. Okay, this is the way by which you will write the truth table, that is n inputs means 2 raised to n input combinations. Then write the outputs. So thereby you got the truth table. Okay, so in all you got the truth table. Second will be, from the truth table you have outputs 1, 2, 3, how many ever outputs you have. For each output, write a expression. Output expression. Write the output expression for each output. So output depends on what? Output depends on input. See, here why is it 0 0? Because the input is 0 0. 0 plus 0 is what you did. Okay, so you are performing some operation on the input to get the output. So the output depends on the input in the case of a combination circuit. So output is related to the input. So in the output expression, what will be there? Output is equal to, what is the right hand side? It will be an expression consisting of the inputs. Okay, for each output, that is in this case you have 2 outputs, so you write an expression for sum, you write another expression for carry, both with respect to the inputs. That is, the right hand side should have a combination of inputs only. Okay, so this is what we are going to do in any combination circuit. So likewise, here also we will write the output expression based on the inputs. Okay, so here what is sum? You need to write 2 expressions. One is sum and the other is carry. So in this case, when a sum is equal to 1, sum is equal to 1 when A is 0 and B is 1, or when A is 1 and B is 0. Right? Just think about the logic. That is, sum is equal to 1 when A is 0 and, right, just because A is 0, the sum is not 1. Only if the sum is A is 0 and B is 1 and B is 1, then sum is 1. But is that the only case where the sum is 1? No. Or there is another case also, or if the sum is 1 and A is 1 and B is 0, then also sum is equal to 1. So this is the expression for sum. So what is A bar B plus AB bar? We know that it is A XOR B. So next is carry. Now what is carry? When is carry equal to 1? Carry is equal to 1 only in one case. Which case? When both A and B are equal to 1. So if we just substitute and see A XOR B. A XOR B is equal to 1 only if A and B are different. If A and B are same, then A XOR B is equal to 0. So that is what is happening here. If both are same, output is 0. Both are same, output is 0. So sum is 1 only if A and B are different. Correct? So if you apply that here, it's correct. And carry is equal to A dot B. A dot B means A and B. So A and B is equal to 1 only if both are equal to 1. In all the other cases, output is 0. So the reverse is also true. So carry is equal to A dot B. So first we drew the truth table. Then we wrote the output expressions. Then we will draw the circuit. So how do you draw the circuit? You have the expression, so you can draw the circuit. So what are the inputs? So you need to know the inputs first. So in this particular case, if you take this particular expression, you can draw it with normal logic gates. You can draw it with NAND only, or you can use an XOR gate. Depends on your question. If nothing is specified, you can go just for an XOR gate. If they say that you have to use NAND only, then go for NAND only. Or if you just feel like drawing with other gates, then draw with other gates. But for lab purpose, if nothing is specified, then it's better to go for the XOR gate, because then you'll finish it off with a single gate. You don't need a NOT gate, OR gate, AND gate, everything. So if you are going with this particular expression, you'll need all those. Even with NAND only also, you'll need two NAND here, two NAND for NOT, and then another NAND for the OR. Okay, so you'll need multiple gates if you go for the normal logic gates or NAND only. If you go for XOR, you just need one XOR gate. And carry is, again, if they don't specify like NAND only or something, you can go for a AND gate. So here it is. If you are, I'm here now going for just XOR gate. So just, I don't need a complement. So this is A, B. So A XOR B will be this is sum, and A and B will be carry. So this total system is called your half adder. So if you are doing it in the lab, what will you be doing? You have A and B as the inputs. So what is your input? Input is normally a switch which you can on and off. If it's in the on position, then it's a 1. If it's in the off position, then it's a 0. Yes. So input is normally we represent it with a switch in the normal labs, right? So here AB, after wiring the circuit, what you will do is you'll see that we'll verify that the truth table is correct or not. So I give 0 0 here, that is both the switch, I'll keep it at off position. So 0 XOR 0. Here the output is an LED. LED will light up if it gets a 1. LED will be off or dim if it is getting a 0. So 0 XOR 0, the output is connected to an LED. Output, what does output come? the output will be 0. So the LED will be off. It's not getting the sufficient voltage. 0 0, again here you have another LED. You have two LEDs. One LED represents one output. One switch represents one input. So here you have two switch inputs and two LEDs as the output. 0 1 means here 0, here also. Here is 1 because 0 XOR 1 is 1. 1 0, here you will get a 1, you will get a 0. 1 1, here you will get a 0, here you will get a 1. So you will be just moving the switches to on and off positions and checking whether the LED is lighting up or not in order to verify the truth table. So that's how you design, set up and verify the truth table of a combination circuit. So moving on from the half adder, next we have the full adder. Now, what is a full adder? Let's just take an example in order to understand the concept of full adder. Suppose we are not going to always add just one bit numbers or something. Suppose you want to add, say, this plus something like this. Okay, so here 1 plus 1 is 0, carry 1. Yes, 1 plus 0 plus 0 is 1. 1 plus 1 is 0, carry 1. 1 plus 1 plus 0 is 0, carry 1. 1 plus 0 plus 1 is 0, carry 1. This is 1 and a carry. This is carry. So such computations are what we are going to normally implement. So in this case, here, see, in these cases, you have a carryover bit from the previous state. Okay, if you take these, each of these as a particular stage, from the previous stage, you have a carryover. In normal addition, it will be there. Okay, so we have to consider that carryover also. In the case of half adder, we are just adding 2 bits and seeing whether there is a carry or not. Okay, we are not thinking about whether there will be a carryover from the previous stage or not. Yes, so if there is, in normal situations, there is a chance that there is a carryover from the previous stage. So in such cases, you have to go for the full adder. So in full adder, you have 3 inputs. What are the 3 inputs? The normal inputs, that is A, B, and the carryover from the previous stage. Okay, so here, if suppose this is say A0, this is A1, A2, A3, A4 and A5, and previous stage carryover, this is C0, this is C0, this is C1, C2, C3, C4 and C5. So if there is no carry, then that carry is taken as 0. If there is a carry, then that is a 1. Okay, so we'll deal with the multiple bits for later on. So this is the concept, that is, this particular one stage, this is represented by a full adder. So in this particular full adder, what do you have? This is B0, this is B1. So A1 plus B1 plus C1. What is C1? C1 is the carryover from the previous stage. So this particular stage is called a full adder. So in the full adder you have A, B, C. C is the previous carry. And output is again sum, which we got as the sum, and carry is the carry to the next stage. This is from the previous stage which you will be adding. This is to the next stage, where in the next stage you will be adding this particular carry. So you have to consider all the possible combinations in this case also. Okay. So you have 3 inputs. So how many input combinations are there? 8. 2 raised to 3 is 8. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 3 is 0, 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1, 6 is 1, 1, 0, and 7 is 1, 1, 1. 0 to 7 is the other 8 combinations. Now what will you do? 0 plus 0 plus 0. That is sum, and if there is a carry, you will write it as the carry. So 0 plus 0 plus 0 is 0, carry 0. 0 plus 0 plus 1 is 1, carry 0. 0 plus 1 plus 0 is 1, carry 0. 0 plus 1 is 1, 1 plus 1 is 0 with a carry 1. 1 plus 0 plus 0 is 1 with a carry 0. 1 plus 0 plus 1 is 1 plus 0 is 1, 1 plus 1 is 0, carry 1. 1 plus 1 plus 0 is 0, carry 1. 1 plus 1 is 0 with a carry 1, and that 0 plus 1 is 1 with a carry 1. That is 1 plus 1 is 0 with a carry. This is carry. This is sum. The next one, this one is added to this. So it is 1, and you have already had a carry. So that is 1, 1. So after drawing the truth table, you have to write the output expression. For what? For both the inputs. So you need an output expression for sum and another for carry. So here you have one for multiple cases. So when you have one in many cases, you have to see whether you can use a K-map to simplify the expression. Okay. Otherwise, what will you be writing here? You have, say, sum is equal to A bar, B bar, C, A bar, B bar, C, or A bar, B, C bar, or A, B bar, C bar, or ABC. Yes. So here you can take the first two. You can take A bar outside, and you can write as B bar C plus BC bar plus A B bar C bar plus BC. Yes, we know that B bar C plus BC bar is B XOR C, and we know that B bar C bar plus BC is B XNOR C. So that will be A bar into B XOR C plus A into B XNOR C. Yes. What is this? This is sum. Okay. So we also know that XNOR is XOR the whole complement. So this can be written as B XOR C plus A into B XOR C the whole complement. So this is like writing, suppose let y equal to B XOR C. So you can write it as A bar y plus A y bar, which is again A XOR y. But what is y? Y is B XOR C. So it is A XOR B XOR C. What is that? Sum. Sum is A XOR B XOR C. So in this particular case, even if you draw the K map, it will be coming in diagonal cells only. So we can't group it with the vertical or horizontal grouping. That's why I explained it like this when XOR or XNOR comes. So after this, carry, but you can see that here in adjacent numbers you have ones. So if you draw the K map, you can solve it, you can simplify it. So you'll be writing the K map for carry. So how many variable K map? Depends on how many inputs are there. So how many inputs? 3 inputs. So it's a 3 variable K map. You are reading it like this, ABC. So A is the MSB. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Yes. So 0, 1, 1. 0, 1, 1. Output is 1. Then 1, 0, 1, 1, 1, 0, 1, 1, 1. All these cases, output is 1. 1, 0, 1, 1, 1, 0 and 1, 1, 1. Or you can write here that sum is a function of ABC such that sigma n here 1, 2, 4, 7. 1, 2, 4, 7. And carry is a function of ABC sigma n 3, 5, 6, 7. 3, 5, 6, 7. So it is 0, 1, 3, 2, 4, 5, 7, 6. So 3, 5, 6, 7. So you have to combine this, group this. So here you can group like this, you can group like this. The best possible grouping is like this, right? So carry, how will you write? Carry is equal to, what is this? BC SOP. BC plus A C plus A B. That is AB plus BC plus AC. So we got the expression for sum and carry. Next we will draw the circuit. So what was our sum? Sum was A XOR B XOR C. So A, B, C. So sum is A XOR B XOR C. A, B, C. So just for theory purpose you can just draw a XOR gate, but practically you don't have a 3 input XOR gate. So normally what you will be doing is, this is an XOR, then you will use another XOR. Okay, so that is, this will be A XOR B, and this is C, so this is A XOR B XOR C, or this is sum. Carry will be AB plus BC, you can take it anyways, okay, plus AC. Whatever comes up, whatever comes down, that doesn't make any difference. You can draw it anyway. Again, for a practical purpose, you don't have a 3 input OR gate. So if you are going in the practical way, you will be ORing this and another OR. So this is carry. Right? Now same thing, we can go for subtractors. Subtractor also you have half subtractor and full subtractor. So first we'll see the half subtractor. Same thing, only instead of addition we will be doing the subtraction. So inputs will be A and B, output will be difference and borrow. Input combinations you'll be subtracting like this, A minus B. 0 minus 0 is 0, no borrow. 0 minus 1, you can't simply subtract 0 minus 1, you have to borrow. Okay, so borrow will be 1. So when you borrow, that is 0 minus 1. So you'll have to borrow. So when you borrow, 0 means becomes 1 0. 1 0 minus 1 is 1. 1 0 is 2. 2 minus 1 is 1. 1 minus 0 is 1. No borrow. 1 minus 1 is 0. No borrow. Okay. Here also, if I am to write the equation for difference and borrow, difference is A bar B plus A B bar. That is again A XOR B, and borrow will be, borrow is 1 only in one case, that is when A is 0 and B is 1, that is A bar B. Now we can draw this. So you have two inputs, A and B. So you have A XOR B, but here you have A bar B. So you'll need a NOT gate. You have to see whether there are any complement inputs, so that if you need a NOT gate. So A XOR B, A XOR B, this will give you the difference, and A bar B, A bar B will give you the borrow. right? So this is your circuit. So in the case of full subtractor, like in the case of full adder, you have 3 inputs, A, B, C, where C is the previous borrow. C is the previous borrow. I'm just notating it with C, okay, for ease of writing. Again, the output is difference and borrow. 3 inputs means 8 combinations, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So 0 minus 0 minus 0 is 0, no borrow. 0 minus 0 is 0. 0 minus 1 is you have a borrow and difference is 1. 0 minus 1 you have a borrow and difference is 1, and 1 minus 0 is 1. You already had a borrow. That is 0 minus 1. You are borrowing. Difference is, this is difference, and you have a borrow, this borrow. Now this minus the 0. So 1 minus 0 is 1. You already have a borrow. That is 1, 1. So 0 minus 1 is 0 minus 1. You are borrowing. Answer is 1. You have a borrow. This 1 minus 1. So answer is 0, but borrow you have. 1 minus 0 is 1. Minus 0 is again 1. Borrow is 0. 1 minus 0 is 1. 1 minus 1 is 0. No borrow. 1 minus 1 is 0. No borrow. 1 minus 1 is 0. 0 minus 1. 0 minus 1. That will be borrow 1, and you have to borrow, then only you will get a 1. So you have a borrow, and the answer difference is also 1. So this is your table, truth table. So you have to write the difference and borrow, right? So I'll just write difference. Difference is a function of ABC. You have to write the full thing. Whatever you are writing here, you have to write. Since I don't have space, I'm not writing. Equal to sigma n 1, 2, 4, 7. 1, 2, 4, 7. It's borrow. It's a function of ABC. Equal to sigma n 1, 2, 3, 7. Right? So you have to write for difference and borrow. So difference you have, again it is 1, 2, 4, 7. So by the numbers itself you can understand that they won't match, like they can't be grouped. So it will be in diagonal elements only, 1, 2, 4 and 7. So they cannot be grouped. So if you check the other one also, 1, what is 1? Difference will be 1 is 0, 0, 1. So that is A bar, B bar, C plus 2 is 0, 1, 0. A bar, 0, 1, 0 plus 4 is 1, 0, 0 and 1, 1, 1. Right? So if you take these two, like in the earlier case, it is A bar B XOR C, and here you have A into B XOR C. So like in the earlier case, it is A XOR B XOR C. What difference? Right? And borrow, like in the case of full adder. Borrow, you have adjacent cells 1, 2, 3, 2, 3 are adjacent cells. So you will be able to group it. A, B, C, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So it is 0, 1, 3, 2, 4, 5, 7, 6. So 1, 2, 3, 7. Yes. So you can group these, you can group these, you can group these. So what is the answer?